B9. So formamide, there was a fair amount of questions that I've gotten, and fielded and tried to answer on Piazza, related to this question right here. And it primarily has to do with people not necessarily thinking about resonance structures, right? You just draw one structure and you're like, my life's done. There's sometimes resonance structures just hiding out, ready to surprise you, and it changes how you have to approach and think about a problem. So, right. So for like formamide, right, the formula is written out right as CH3NO. That's not how the bonding is, right? I described the bonding in the next part, so you just have to pay attention to that. So in this case, right, it has one hydrogen atom, the nitrogen and the oxygen attached to the carbon, right? So that means that in this case, right, we have a carbon in this case, and so then we have one hydrogen, one nitrogen, and one oxygen bound to the carbon in this scenario, and then the two remaining hydrogen atoms are attached to the nitrogen, right? So we have hydrogen here and hydrogen here. So now we just need to finish working out the octet rule, right? So if we look here at the carbon, right, this carbon still has one more electron that hasn't done anything, right? This oxygen has 1, 2, 3, 4, 5, right? So it has two lone pairs and one unpaired. So that means that you're going to get a double bond between the carbon and the oxygen, right? This nitrogen has 1, 2, 3 around it, right? It's still missing two electrons, right? And so those are going to be a lone pair there, right? So that right there is a completely valid, structure for formamide in this case. Now, the thing that's throwing people off, right, is that they're not thinking about the resonance structure. Because if we're looking at this right here, you can draw a resonance structure of it where all the bonding, right, all the single bonds all stay exactly the same. The only difference is that you're moving the double bond in this case. And so anytime you have a lone pair that can, next to a double bond, there's a very good chance that that lone pair is actually part of a resonance structure, where that double bond then moves, right? So in this case right here, right, if this moves, what we get is then now that oxygen, right? So the lone pair from that double bond between the carbon and the oxygen moves onto the oxygen, and so now that oxygen has a formal negative charge, right? But now the lone pair from that nitrogen moved into the bond to form a double bond between the carbon and the nitrogen in this case. Right, so we have this, you still have the two hydrogens here, and so now the formal charge on that nitrogen is a positive charge, right? But it's a completely valid resonance structure, right? It overall the molecule is still neutral. The oxygen has a full octet, right? It has a negative charge, so it would it's the most electronegative atom out of all of them, so that makes the most sense, right? The carbon has a full octet, the nitrogen has a full octet, right? It has a positive formal charge. In this case, right, which is perfectly fine and acceptable, right? And so those are the resonance structures in those cases. And so, that tells us then that what the hybridization is of everything is that, for this carbon, right, and this oxygen, just from that first resonance structure, right, you'd be able to figure out that it's sp2 hybridized. But you're probably going to get tricked thinking that because that nitrogen in that initial structure only has a lone pair on it, right? You'll be like, oh, well, this has to be sp3 hybridized here, but that's not the case, right? Because you can draw the resonance structure where now that lone pair can form a double bond between the nitrogen and that carbon, right? In that case, and so now, right, that's how you find out that this is then, sp2 hybridized. And the thing is too, right? If you were to draw the resonance structure, the one on the right, and look at that, in isolation all by itself, you would then look at it and be like, oh, well, that oxygen is sp3 hybridized now because it has, 3 lone pairs around it and one bonding domain. So it has to be sp3 hybridized. But again, that's not true because, that one of those lone pairs is actually part of the resonance structure, right? It's part of that conjugated system, in those cases, right? So the carbon, the oxygen, and the nitrogen, they're all actually sp2 hybridized. They're not just simply, switching between sp2 and sp3, right? The only way that you're switching between hybridizations is if there's like a real chemical reaction that's happening where something is coming in and either, pulling out electrons from something, or you're forming brand new bonds, in those cases, right? Those are the only two ways that you're really going to be changing out any of the hybridization for what you have. Right. And so then now, part B is like, if you built a model of this molecule, would you expect it to lie flat on the table or have a puckered structure, right? So you would expect it to lie flat, right? Because the, carbon is trigonal planar, right? The oxygen is trigonal planar. The nitrogen is trigonal planar, right? Because they're all sp2 hybridized, right? And the hydrogens are just there, right? And so you would expect it to lie flat, right? You wouldn't expect it to have the puckered structure where one of the atoms was sp3 hybridized, right? Because they're not. They're all sp2 hybridized. And so that's the thing, right? When you're drawing resonance structures, you know, you have to look into whether or not you can move a lone pair, or you can move a double bond, right? So that a lone pair comes in and binds to something, and forms new interactions in those cases. So, yeah.